Now, of course, reactions that have a positive cell potential can be utilized in galvanic cells to actually generate an electrical current. So again, not a whole lot of basic concepts in this, just applying them in many ways. So I'll be whizzing through it, not at a ridiculous rate, but certainly I'm not going to dwell on every question. So we'll start off with which is of the following not a necessary component of a voltaic cell. Voltaic cell is, of course, the synonym for a galvanic cell. And here is the standard process, right? You start off with an anode in which oxidation is going to occur. You have a cathode in which reduction is going to occur. Both of these electrodes, or both of these half cells, contain a mobile phase and a stationary phase. The stationary phases are linked by a wire, and it's through that the electrons travel. The mobile phases, usually solutions linked by some kind of salt bridge that allows neutrality to be maintained. So what we see at the anode is it loses electrons, so it's losing a negative, so it needs an anion to come in to help it balance that. Over here on the cathode, it's gaining electrons, so it's gaining negatives, so it needs a positive, a cation, to come in to balance that out. So anyway, let's see what we've got here. Okay, we first of all have got two conducting electrolyte solutions. Those are the mobile phases. We have a conducting path for electrons between the anode and the cathode. That's known as our wire. We have, of course, a cathode because it's nicely labeled, and an anode because it's nicely labeled. The one thing we don't have is a voltage source, because that's the whole point of a voltaic cell. It is a voltage source. It doesn't need a voltage source. And needing a voltage source makes it an electrolytic cell. Which is always correct about the cathode in galvanic cells? Well, by now I hope you know that cathodes is where reduction occurs, and electrons are going to travel to the cathode from the anode, because the cathode gaining electrons, because it's a reduction, it needs those electrons. Where does it get the electrons from? From the oxidation, which takes place at the anode. So statements 2 and 4 are correct about the cathodes. Statement 1 is true of an anode, and statement 3 is, I guess you could sort of say that's true of an electrolytic, but really not. So 3 is totally bogus, 2 and 4 cathodes, and 1 anodes. Question 30, which pair of the following half reactions will produce a galvanic cell with the highest potential when coupled? Well, a galvanic cell, of course, you need one reduction and one oxidation, and you need the overall cell potential to be positive. So what you do is you take the more negative reduction that's there and you flip it to turn it into a more positive oxidation. So therefore the aluminium is the most negative in terms of the reduction, so we're going to flip that, and the most positive is the one we like for the reduction, so we use that. So therefore the silver plus going to silver is the best reduction. Al3 plus coming from Al is the best oxidation, or in other words, Al going to Al3 plus is the best oxidation. Put those together and you will get the best galvanic cell. So consider a voltaic cell based on the half cells. Notice both of these half cells are listed as reductions. Well, if we're going to have a voltaic cell, we need a reduction and an oxidation. So we've got to flip one of these half equations. Now we want overall, of course, as a voltaic for the overall cell potential to be positive. So therefore we need to flip the one that is the more negative or the less positive. So in this case here, that's the copper. So we'll be flipping the copper one and we'll be leaving the silver as it is. So the reduction will be silver, and that's 0.8. The oxidation will be the copper 2 plus getting flipped to give us the copper. So starting with the copper going to the copper 2 plus. It was plus 0.34, so now it's going to become minus 0.34. So therefore, putting all those together, and the cell voltage under standard conditions plus 0.46 volts. Identify the cathode. Well, the cathode is always where reduction takes place, so it's going to be the silver plus going to the silver. Do notice that if I'd flipped instead the silver to make that the oxidation, I would have had minus 0.8 and plus 0.34, which would have given me minus 0.46 volts. Always flip the smaller one, the one that is the less positive or the more negative. You've got a pretty little cell here, right? Given that E red for zinc 2 plus is minus 0.76 volts and reduction for Ag plus is plus 0.8 volts, in which direction do the electrons flow? Well, when we look at what we've got here, we've got zinc and zinc 2 plus, and we're told that the reduction potential for that is minus 0.76. We also have silver and silver plus, and we're told the reduction potential for silver going to silver plus is plus 0.8 volts. So one of these has to be flipped. Which one do we flip? We're going to flip the one that's more negative, so that's going to be the zinc. So instead of having zinc 2 plus going to zinc, we'll have zinc going to zinc 2 plus, and the potential for that will be plus 0.76 volts. So in other words, the zinc is going to be the oxidation, which makes this the anode. The silver is going to be the reduction, which makes this the cathode. And electrons flow from the anode to the cathode. So therefore, they're going to flow from the zinc through the wire to the silver. Galvanic cell based on two redox couples, nickel 2 plus and Cr3 plus. We've got the two E values below. There's the nickel 2 plus, minus 0.25. There's the Cr3 plus, minus 0.74. Well, if it's a voltaic cell, we are obviously going to have one of these reductions is going to be flipped to give us the oxidation, and we flip the more negative one, so that will be the chromium. So therefore, now we can say reduction is going to be the nickel. We leave that as it is. And the oxidation is going to be the one we flipped. Instead of Cr3 plus 3 electrons to Cr, it's Cr goes to Cr3 plus 3 electrons. Oxidation takes place at the anode. Reduction takes place at the cathode. Okay, so we can put in for the anode there, the solid one is the chromium, and the solution is Cr3 plus, and at the cathode for the reduction, the solution will be Ni2 plus, and the stationary phase, the solid, will be nickel. So now let's see what's going to happen. We're looking for the correct statement. So is the direction of electron flow from nickel to chromium? No, electron flow goes from the anode to the cathode, so therefore this is false. Anions in the solution migrate towards the nickel electrode. Well, the idea is that electrons go down into the nickel and attract to them the Ni2 plus. So therefore it's the cations that migrate towards the nickel electrode. Okay, and then they're replaced with cations from the salt bridge. So that one's false. Chromium serves as the anode. Absolutely, we've just demonstrated that. The net cell is 3 nickels plus 2 Cr3 pluses goes to 3 Ni2 plus 2 chromiums. Well, here is overall the equation. We've got nickels that need 2 electrons. We've got chromiums that produce 3 electrons. So we got to have 3 of the reductions that use up 6 electrons with 2 of the oxidations that produce 3 electrons. So there's the overall equation here. And you can see that this is flipped. E cell is 0.99. Well, let's have a look, shall we? The nickel is minus 0.25 because that's the one that's being reduced. The chromium, though, we flipped, so it's not minus 0.74 anymore. It's plus 0.74. So add those together, and the E cell is actually 0.49 volts, so that is also false. So the one that's true is that chromium serves as the anode. That was, I think, a rather tricky question that really tests your comprehension of many concepts associated with galvanic cells. Consider the following half equations, their potentials, and then give the line notation for a voltaic cell based on these half equations. Well, again, voltaic has got to be positive E, so therefore we're going to have to flip the more negative reduction to turn it into the better oxidation. Well, the manganese is the more negative reduction, so therefore we'll flip that around. So we've got Mn goes to Mn2 plus at plus 1.8, and so that is the anode. And of course, the cathode is therefore going to be the chromium 3 plus going to chromium again. What we've done so many times, we got 2 reductions to make a voltaic cell. We flip the one that has the smallest, the more negative of the reduction potentials to turn into the best oxidation potential. So manganese is the anode, chromium is the cathode. So on the left-hand side of our cell notation, we write the anode, and then 2 lines, and on the right-hand side, we write the cathode. So there we are, Mn goes to Mn2+, Cr3+ goes to chromium. Instead of the nice little 2-way arrows, we replace that with straight lines because we're going from solid to solution, solution to solid. We have a phase change. Now, I also wanted the standard cell notation. Standard cell notations means if you've got solutions, they are 1 molar. So therefore the correct full notation, there's the anode, there's the cathode, noting that the solutions are 1 molar. So which statement correct about this electrochemical cell? Well, we always write the anode on the left and the cathode on the right. So the anode, the oxidation, silver going to silver plus, the cathode, the reduction, NO3- going to NO. So let's look at the possible statements. Does Ag undergo reduction at the cathode? No, Ag undergoes oxidation at the anode. Does NO undergo oxidation at the cathode? Well, first of all, NO is associated with the cathode, and it's the product of the reduction. So NO is produced by reduction at the cathode. Silver electrode decreases in mass as the cell operates. Well, the half equation is silver going to silver 2+. So therefore, we're actually using up the silver, so the mass would decrease. So that actually looks pretty good and positive and correct. But let's continue on. The voltage of the cell can be doubled by doubling the size of the Ag electrode. Well, this is a solid. Solids don't appear in equilibria calculation, so it's not in Q, so therefore it would have no linear relationship at all between the silver electrode size and the voltage. And finally, what's the platinum there for? Well, it's an inert electrode because you've got the components of the cathode are both in solutions, both aqueous, so you have to have a solid phase. So that's the only one that is correct. The Ag electrode decreases in mass as the cell operates. That's in a nice pretty red.